integrate, and believe it or not, that is much, much simpler to integrate, and it actually has a very simple form. Okay, so what I'm going to do in order to evaluate this is I'm going to expand this term using the binomial expansion theorem, or whatever it's called. So a plus b to the power of n is the sum from j equals 0 to the n of n choose j, a to the power of j, b to the power of n minus j. So now a term of what we have here, 1 plus t squared to the power of n minus 1, obviously because when we're adding, it doesn't matter what order we do it within. That's the same as t squared plus 1 to the power of n minus 1. So just following this form, we have a is equal to t squared, b is equal to 1, and n is equal to n minus 1 in this case. So that becomes the sum from j equals 0 to n minus 1 of n minus 1 choose j. Remember, n gets replaced with n minus 1. And j, our a term, as we just went through, is t squared, so t squared to the power of j. And then we've got b here, which remember is 1, as we went through before, to the power of n minus j, which is n minus 1 minus j. Excuse me for a second. My apologies. As I said, I'm still suffering from the flu. Okay, so 1 to the power of anything is obviously just 1, so that's why that term just gets absorbed. And then just expanding it out using our indices laws here, we've got the sum from j equals 1 to n minus 1 of n minus 1 choose j, t to the power of 2j. So I'm going to plug that into our integral now. And we see the integral from 0 to infinity of 1 plus t squared to the power of n minus 1 over t to the power of 2n plus 1. Sorry, one thing that I did not mention before is that when it comes to this binomial expansion, that is when we're dealing with an integer power of n. Now remember before, we have this defined for an integer power of n. In fact, a natural number, so a positive integer, which is actually very important as well. So this binomial expansion only works in this instant because n is already a positive integer, or in this case, restricted to a natural number, so 1, 2, 3, 4, 5, 6, and so on. Okay, so that gets replaced with the term that we had before, that we went through just before, I should say, sorry, which we have within here, the sum from j equals 0 to n minus 1 of n minus 1 over j, t to the power of 2j. And then all I've done is taken the linearity property of continuous integrals, and the integral of a sum is the sum of the integrals, which is what we have here. So we can drag this sum out the front, and we have the sum from j equals 0 to n minus 1 of n minus 1 choose j, because remember this is just a constant, it doesn't have any t terms within it, so it's not part of the integrand. And then what's left over is the integral from 0 to infinity of t to the power of 2j over t to the power of 2n plus 1 dt. So just that term that is remaining there. And the reason why it remains there is because it's got a t. Okay, so this is a very common integral, so I'm going to draw upon its known result. This is one that I have been really meaning to upload soon, but if it's a very well-known integral. It's something that is used a lot. If people want to see the video that actually shows this integral, as soon as possible, if they prefer to see it within my next video, for instance, again, please just send me a direct message or comment on here, or send me a message on my Facebook page, and there will be a link to that in the comments. Let me know, and I'll certainly do up a video for it. It's been something I've just been putting off. Okay, so as I said, we're going to rely on this integral here, which is a generalized integral, so it actually complicates this a little bit further to go into a general form, which is the integral from 0 to infinity of t to the power of k over t to the power of n plus a, where a is a positive constant, all to the power of m. Now in this instance, I can't remember the exact rules for convergence, but definitely what we need to have is that m has to be a positive value, and n and k, if I remember, have to be real values that are greater than 1, and a has to be a positive value. So they are the definite restrictions. You may actually be able to relax those a little bit, but if we impose those restrictions here, they definitely allow for convergence to occur. And most importantly too, they'll also be satisfied within the form that we have. But it equals this expression that we have here, which is a to the power of k plus 1 over n minus m over n times by gamma of m times by gamma of m minus k plus 1 over n times by gamma of k plus 1 over n. So again, it's a very generalized, sort of may appear to be a little bit of a nasty form, but quite often when you're dealing with cases such as this, you can employ some rules to actually simplify it. Nice thing about this is it just accounts for so many different cases. Anyway, okay, so in our situation here, we need to evaluate it for t to the power of 2j. So in our case, our k term is equal to 2j. So that's all we have within here. So this integral here, actually, probably better if we go here, which is what we've got from before. J is sum from j equal, let me start again. The sum from j equals 0 to n minus 1 of n minus 1 choose j, the integral from 0 to infinity of t to the power of 2j over t to the power of 2n plus 1. Comparing it with what we have here, we see here that firstly our a term, so in terms of the integral, is just 1 because we've got plus 1 here. And the constraint that a is a positive real value is satisfied. Great. The next component that we want to have is our k term, and our k is whatever's on the top that t is raised to the power of. We've got 2j, which is what we have here. Our n term here is what we've got t to the power of n on the bottom. So in our case, n is equal to 2n, which is what we have here. And then our m term is the power of that component on the bottom, in the denominator, I should say. And in our case, this is obviously just the same as it being raised to the power of 1, so we have n is equal to 1. Okay, so now we're just going to plug in our formula from here. And so this becomes a sum from j equals 0 to n minus 1 of n minus 1 choose j, 1 to the power of, so what we have here, k plus 1 over n, which is 2j plus 1 over 2n, minus n, which is minus 1, over n, which in our case is 2n, times by gamma of m, which in our case is gamma of 1, times by gamma of m minus k plus 1 over n, which in our case is 1 minus 2j plus 1 over 2n, times by gamma of k plus 1 over n, which again, in our case, is gamma of 2j plus 1 over 2n. Okay, so this term here, 1 to the power of something, we know 1 to the power of anything when we're dealing with real values is just 1, so that disappears. This gamma of 1, which is 0 factorial, is just 1, so that disappears as well. And this 2n term, because it's got nothing to do with the sum here, because the sum is indexed over j, we can bring that out the front. So what we're left over with is the sum from 1 over 2n, 1 over 2n, sorry, the sum from j equals 0 to n minus 1 of n minus 1 choose j, times by gamma of 1 minus 2j plus 1 over 2n, times by gamma of 2j plus 1 over 2n. Now, if you wanted to leave the solution like that, that's perfectly fine. It's 100% valid. But thankfully, because there's some nice properties here, we can actually simplify this down a little bit further. So, firstly, we've got a form that is something that immediately jumps out at me because I've used it a lot. But we've got the form of gamma of 1 minus something times by gamma of something. So if this was z, 1 minus z times by gamma of z. And immediately what jumps out to me, because I've just seen it so many times, is Euler's reflection formula. So that's what we're going to use here. So Euler's reflection formula, when applied to the gamma function, states that gamma of z times by gamma of 1 minus z, which is the form that we have here, is equal to pi over sine of pi z, but the restriction is that z cannot be an integer. So that's the form that we have here. So if we were to apply, in our specific instance, z is equal to 2j plus 1 over 2n, and so therefore plugging it into this formula, we have pi over sine of pi times by z, which is 2j plus 1 over 2n. Now this only holds if 2j plus 1 over 2n is not an integer. So we need to make sure that that is the case. Thankfully it is the case in our situation. Remember, n is a positive integer value. So 1, 2, 3, 4. So 2 times n is always going to be an even number. 2, 4, 6, 8, 10, 12, whatever. 2j plus 1, well, j is always a positive integer as well, starting at 0 and going up to n minus 1. So that means that 2 times by j plus 1 will always be an odd number. So what we've got in terms of our z value here is on the numerator we've got an odd number, and then on the denominator we have an even number. Odd and even, they will never cancel out to be an integer number. So have a think about it. No matter what you have, if you have an odd on the top, on the numerator, and an even on the bottom, that will always be a fraction. And what's important about that is that that fraction will never be an integer component. And why that's important is because we need that to be satisfied in order to use Euler's reflection formula, which we have satisfied here. So therefore, we are allowed to use this. And just, I want you guys to be very aware of that when you're going through these sorts of videos, because quite often you'll see this, it'll be stated as being used, and then they won't state this, restriction. And so you think that this just holds for any value of z. If you're not told, then you're not going to know. And, that can lead you into problems later on if you then go, oh, yeah, okay, well, I've got, 5 times by 1 minus 5. Yeah, I can use that. No, you can't. So just to be mindful of whatever restrictions are imposed. Same as I was going through before when we were using this general formula. As I said, the conditions that I spoke to, A being positive, M has to be positive, and I'm pretty sure N and K have to be positive and greater than 1. As I said, we may be able to relax those down a little bit further, but definitely A is greater than 0. Definitely M has to be greater than 0. N and K may be something that it is greater than 0, but I definitely know for certain that if they are real values and greater than 1, then it will definitely work, as we have satisfied in our situation here. Okay, so as I said, what we're going to do is we're now going to replace this term with this term here, and what's beautiful about that is that we've taken it from a multiplication, of non-elementary functions, which are the gamma functions that we have here, and we've converted it into an elementary function. So for me, I know I've said this in other videos, for people who may have watched my other videos, whenever I can put the solution into the form of an elementary expression, I always strive to do that. Now, that is not the case in many situations, and that's just, part of life. But wherever we can put it into an elementary form, it's best to do that. Or at least I believe it's best to do that. Okay, so plugging it in. So I of n, the integral that we had before, which we had resolved down to this expression from here before, as we just went through, these two gamma terms get replaced with this, which is what we have within here. And so obviously this pi term here, because it's a constant, we can just bring it out the front. So that's where we've got the pi over 2n here. And what we're left with is the sum from j equals 0 to n minus 1 of n minus 1 choose j. Remember, 1 over sine is just equal to cosec. If you wanted to leave it as 1 over sine, that's perfectly fine. I'm just putting it as cosec just because I want to. And then all I've done is just change it a little bit. You'll see here that I brought this 2n out to the front here. So out to the side. To the back, I should say, pi over 2n, and then what's left over is this 2j plus 1. If you had left it in this form, obviously these are two ways of saying the exact same thing. And so therefore, in summary, I of m, which is the integral from 0 to pi over 2 of 1 over sine to the power of 2n of x plus cos to the power of 2n of x dx is equal to pi over 2n, the sum from j equals 0 to n minus 1 of n minus 1 choose j times by cosec of open brackets 2j plus 1 multiplied by pi over 2n, where n is a natural number. So I hope you've enjoyed this video. This is one that when I got it out, I was actually really excited to get this one out. This is one that I really enjoyed because I never thought when I first looked at this that I would actually be able to resolve it down into elementary functions, but we have been able to do that, so that's just fantastic. If you have enjoyed the video, please like the video. If you'd like to see more videos like this, for anyone who is following my channel, you'll see that it really is a great mishmash of different types of integrals. At this stage of the lifetime of the channel, I'm just putting up things that I think people will be interested in. But if you have specific requests that you would like to see gone through, please send me a message.